Hello everyone, our today's topic is set theory. The topic begins with a basic definition of set and some basic notations. So let's begin with what is a set. A set is any well-defined collection of distinct objects. With the word well-defined, we mean whenever we define a set, the definition of the set has to be well defined. Nothing but suppose I define a set A as collection of vowels, then this definition is well defined. But if I define a set A as collection of suppose intelligent students of the class, then this definition is not well defined, because according to me a student may be an intelligent, but according to another teacher that student may not be intelligent. So here the definition is not well defined, so we need not consider this kind of definition to define a set. And also you can see we have written the collection of distinct objects. Nothing but whenever we have a set, that set should consist of distinct objects. Nothing but if there is repetition, we should remove that repetition. We should have each element exactly once in the set. Okay, so let's talk about definition, notation. Usually sets are denoted by capital letters. Nothing but we can denote our sets by capital letters A, B, C, X, Y, Z or P, Q, R, like, okay. And the elements of the sets are denoted by small letters. We can use small letters A, B, C or P, Q, R or X, Y, Z to denote elements of the sets. Let's see some examples. So I have a set A over here which is having members as A, E, I, O and U. I have another set B as 2, 4, 6, 8 as the members. Now let's talk about belongs to and does not belongs to notation. Suppose A is a set and X is a member of that set A, then it can be denoted by X belongs to A. X belongs to A means X is a member of set A, and if X is not the member of set A, we can denote it as X does not belongs to A. Nothing but X does not belongs to A means X is not a member of set A. For example, suppose this is our set. So here we have members of A as 2, 4, 6 and 8. So we can say 2 belongs to A, 6 belongs to A, 8 belongs to A, etc. because they are what? Members of set A. But 3 is not the member of set A, so we can say 3 does not belongs to A. We can say 5 does not belongs to A because 5 is not the member of A. Okay, so belongs to is basically for saying something is a member of that set, and does not belongs to means we use for saying something is not the member of the set. Okay, now set rooster notation. So basically we use two representation to denote sets, to define, to write a set, to represent a set. One is set rooster notation, another is set builder notation or the property notation. Okay, What is a set rooster notation? So what we do over here in set rooster notation, we write all the elements of the set between the braces. Okay, that's what a set rooster notation. So what we do in set rooster notation, we write all the elements of the set between the braces. For example, okay, so here I have written all 4 members of the set between the braces. It may not be possible to write all the elements of the set because sometimes your set may be too large. So if it is too large, you can't keep on writing each and every element of the set. So in that case, we either write some of them so that it will be clear what kind of elements are there in the set, okay, and sometimes we write that set in set builder form. Okay, for example, so here I have a set B which is large enough, so I am not writing all the elements over here. I have written some of them so that there is some pattern followed by these elements. Okay, so after writing some element, that pattern has to be clear for whoever is reading. Okay, so you can see I have written just 1 3 5. So whoever is reading, that person will understand what will be the next element. Okay, and this is a finite set, so there has to be some endpoint. So for this one there is a endpoint 99. That means you have to follow the pattern, but you need not go beyond 99. But we may have infinite set. For example, over here in this one we have infinitely many members, but there is a pattern followed. So I have written some elements, and if we look at the elements, you can understand what will be the next elements. But since it is an infinite set, there is a no stop to it. There is no number like 99 over here. It going, keep on going, dot dot dot. Okay, so this is how we write in set rooster notation. Now let's talk about some basic and important sets, which are very important while studying set theory. Number 1, set of integers. It is denoted by script Z. Set of natural numbers denoted by script N. This set can also be said as the set of positive integers and can also be represented as written as Z plus, can be denoted as Z plus. The set of whole numbers denoted by script W. The set of real numbers denoted by script R, and the set of positive real numbers denoted by script R plus. So these are some of the most important sets which we should know from the beginning itself, so that wherever it is written we should understand that denotes what. Okay, now let's talk about set builder notation. What is set builder notation? So whenever we define a set, the elements of the set may follow some property. The element of the set may have some property. So in that case we use this set builder notation, also known as set property notation. Okay, so this is nothing but the set builder notation. What we do in set builder notation, we write the curly braces and we write the x and we write this straight line which is read as, which we read as such that. And this full thing, how to read? This full thing we can read as the collection of all those x such that x has a property P. The collection of all those x such that x has property P. Okay, so this is how we read this set builder notation. For example, suppose I have this set A. So I have to understand what is the property these elements have. So if I think over the properties followed by these elements, what I can note here, the elements are integers, number 1. Number 2, they are even integers, and number 3, they are integers between 2 and 8, where 2 and 8 are included. So I can write this A as collection of all those x such that x is an even integer and x is greater than or equals to 2 and less than or equals to 8. There can be many ways of writing the same thing in set builder notation, and this is one of that. Okay, suppose I have example B. I have a set B like this. Then again I have to think on what are the properties satisfied by these elements. So if you observe, the elements are integers, they are odd integers, and they are between 1 and 99. So I can write this B as collection of all those x such that x is an odd integer and x is greater than or equals to 1 and less than or equals to 99. Now let's talk about subset. Suppose we have two sets A and B, then A is called subset of B and we denote it by this symbol. Okay, this you have to read as A is subset of B. So A is subset of B if and only if every element of A is also an element of B. If every element of A also element of B, then A is called subset of B. Nothing but all the members of A are also the members of B, then A is called subset of B. Let's see examples. So here I have a set X which is 2, 4 and set Y which is 1, 2, 3, 4, and you can see over here all the members of X are the members of Y. That is why we can say here X is subset of Y. Let's see another example. So you can see I have a set A as a collection of all those x such that x square minus 9x plus 18 is equals to 0, and set B as a 0, 3, 6, 9, 12. Now if you see this set A, that set A is not having explicit members right now. We can't see members of A explicitly. So to get this members of A explicitly, we are supposed to solve this quadratic equation. And how to solve this quadratic equation? To solve this quadratic equation, we do factor of plus 18. So we have to get factor of plus 18 in a such a way that multiplication will give you plus 18 and addition will give you minus 9. And what is those numbers? Those numbers are minus 3 and minus 6. because minus 3 into minus 6 will give you plus 18, and if you add them, minus 3 plus minus 6 is minus 9. So that is why x becomes 3 and 6, because these are what? Factors. These are what factors means you get x minus 3 and x minus 6 equals to 0. And if you equate each term to 0, you will get the values of x. So from this first one you will get value of x as 3. From the second one you get value of x as 6. So basically the negative of factors are nothing but the values of x. So we get values of x as 3 and 6. So that is why our a becomes 3, 6. So we can write a in set rooster notation as 3, 6. And now we can see the members of A are the members of B. So that is why we can say A is subset of B. Okay. Now let's go next. Now we will talk about when can we say A is not the subset of B. So recall, when do we say A is subset of B? If all the members of A are the members of B. So if we lack at least one member which is not the member of B, if we get at least one member of A which is not the member of B, then we can say A is not subset of B. Okay. So when can we say A is not subset of B? If we get at least one element in A which is not in B. Okay. For example, so I have a set X and set Y, and if you observe, members 2 and 4 of X are also members of Y, but member 6 is not the member of Y. There is no 6 in Y. Okay. So we got one member which is in X but not in Y. Okay. We have got one member of X which is not the member of Y. That is why X is not subset of Y. Okay. Let's see another example. So I have two sets again. Set A is written in set builder form and set B is written in set rooster form. Let's have set A in set rooster form. To get set A in set rooster form, we have to factor this minus 18. So we have to factor this minus 18 in such a way that multiplication of the factors will give you minus 18 and addition of the factors will give you minus 3. Okay. And what are those numbers? 3 and minus 6. If I multiply 3 and minus 6, I'll get minus 18, and if I add 3 and minus 6, I'll get minus 3. So this is the required factor, and as you know, negative of factor is the value of x. So x equals to minus 3, 6. So that is why A becomes set with two members minus 3 and 6. And after that we can see we have a member in A, we have an element in A which is not in B. We have a member in A which is not in B. That is why A is not the subset of B. So I hope the concept of subset and not subset clear to you all. So let's talk about proper subsets. When can we say a subset is a proper subset? Okay. So basically that set has to be subset first of all. Okay. And there is one additional condition There is one additional condition on that subset to say that is a proper subset. So what is a proper subset? A is said to be a proper subset of B if and only if every element of A is in B. Every element of A is in B. It means we are talking about A is subset of B. You should have A is subset of B. Okay, but there is at least one element of B that is not in A. This is the extra condition which is imposed over here to say that is a proper subset. So what is the extra condition on the subset? We should get at least one element in B, at least one extra element in B which is not present in A. Okay, so that will be called as proper subset. And a subset which is not proper will be called as improper subset. Okay, so a subset will be either proper or improper. If it is not proper, then it is improper. Okay, let's see examples. So I have a set X and a set Y, and you can see two things we have to satisfy to say it's a proper subset. Number one, X is subset of Y. Number two, Y is having extra element. Okay, so let's check this one. So we have 2 and 4 in X, we have 2 and 4 in Y. So that means X is subset of Y. Number 1 is done. And number 2, Y is having extra element. Do we have extra element in Y? Yes. We have 1 belongs to Y, which is extra, I can say, because it is not present in X. So that is why here I can say X is proper subset of Y. Okay, and this is the notation used to write a proper subset. What is written? If it is not clear, I am writing over here. This is how you have to write. Below the subset notation, there is a line which stands for equality. That you have to cancel to say it's a proper subset. And in some of the books, you may find it as this. There is a equality sign which is cancelled. Okay, to denote a proper subset. Let's see another example. So here I have another example. I have a set A in set builder form, set B in set rooster form. So I have to write that set A in set rooster form first. To do that, I'll have to factor this plus 18. To factor this plus 18, we want two factors such that multiplication will give plus 18 and addition will give minus 9. And that is what? Minus 3 minus 6. And this will give me X as 3 and 6. So what we have got? We have got A as 3 comma 6 in set rooster notation. And what after that? This A is subset of B. So here A is subset of B. So point number 1 is done. Point number 2 is what? The other set should have extra element. So if you see, B is having lots of extra elements. There is a 0 in B which is not there in A. So I can say what? I can say A is proper subset of B. Okay, so let's see one example of improper subset. When can we say a subset is improper? Okay, to say a subset is improper means we should have a subset, and number 2, that subset should not be proper. Okay, so I have a set C over here, you can see in set builder form. So I'll have to solve this to write in set rooster form. To solve this, I have x square minus 9 equals to 0. So x equals to plus or minus 3. Nothing but x square is equals to 9. So x is equals to plus or minus 3. Okay. So that is why C in set rooster notation minus 3 comma 3. And now if you observe, we have C subset of D, because all the members of C are the members of D. But do we have extra member in D? No, we don't have any extra member in D. So that is why this becomes improper subset. Okay, if we have an extra element, then it's a proper subset. If we don't have that extra element, then it's improper subset. And if I say clearly over here, our C is equals to D, which I'll tell you in the further slide. So here C is improper subset of D. Okay, now let's talk about empty set. What is an empty set? A set without any elements is called an empty set. A set which is without any member, okay, that will be called as empty set. It is denoted by either a Greek letter phi or the curly braces without any members. Okay, you should not have anything inside that curly brace. So this is what an empty set. For example, suppose I have a set X which is defined this way. Okay, now to get this, what I'll have to do, I'll have to solve this equation. So I have this equation 2x is equals to 5. So this will give me x is equals to 2.5. But what is written over here? X belongs to z. If I read it properly, what is written? Collection of all those x such that x is an integer and x follows this equation. So x follows this equation, so that this will give me the value of x. But along with that, x has to be integer, but this x is not an integer, so that means there is no such x. Okay, the x which we are talking about here, collection of all those x such that it satisfies this property. We are talking about such x which has this property 1 and this property 2, that is that they are the members of this set X. But if we solve this, we come to know that there is no such X. We don't have integer value to satisfy this equation. Okay, so that is why this X becomes empty set. There is no member, there is no such X exist. So that is why X becomes empty set. For example, another example, let's say another example. So we have another example over here, collection of all those x such that x is a natural number and x satisfies this property. Okay, this quadratic equation. So let's solve this quadratic equation. In quadratic equation we have plus 18, we have to find out factor of it. So the factors will be 3 and 6, because 3 into 6 will give plus 18 and 3 plus 6 will give plus 9. If the factors are 3 and 6, then the roots will be minus 3 and minus 6. And what is your property 1? Property 1 is saying x has to be integer, natural number. X has to be natural number, but these are not the natural numbers. So only these two are the possible solution and they are not the natural numbers. So that is why there is no such x. There is no x which is natural and solution of this quadratic equation. Okay, that is why this set A becomes empty. You can see in example 1 I have denoted empty set like this, and in second example I have denoted empty set like this, we can use any one of the two. Either we can use the Greek letter phi, or we can use curly braces without any member in it. Okay. And one very important note point over here, empty set is a subset of A for any set A. For any set A, empty is a subset. Okay. So you can say in general, if you have any set A, we are not aware of what are the members, what all things we have in A, we can say empty is subset of that set A. And how this happens? This happens basically with the help of the definition of subset. What is the definition of subset? The definition of subset says whatever members are there in this has to be present in this. But what are the members inside this phi? There are no members. If there are no members, we need not check that is present over here or not. Okay. For example, suppose I have set A is equals to 1. I have set B is equals to 1 comma 2. And I want to say A is subset of B. So I have to check whatever members A is having, they are members of B as well. So if I go inside, I have a member 1. So I have to check that 1 is present in B or not. Okay. But here in this case, that this empty set is not having any member. If there is no member, there is no need to check. So we can trivially say the empty set is a subset of A. Okay. Now let's go to the next. So here we will talk about equal sets. When can we say the two sets are equal? The two sets are said to be equal if they have same elements, and we write it as A equals to B. For example, suppose set A is 2, 5, 3 and set B is 2, 3, 2, 5. Then we can rewrite this set B as 2, 3, 5 because there is a repetition of member 2. And when we say a set is well-defined collection of distinct objects. Okay. So that is why we will remove this repetition. So we can rewrite this set B as 2, 3, 5. And now if you see, your A is having members 2, 5, 3, your B is having members 2, 3, 5, they both have same members. And here order does not matters. Okay. We are just talking about members. In what order members are appearing, that is not important when we talk about sets. In the sets, we don't worry about the order. We only worry about the members. What are the members? So that is why here we can say A is equals to B. So I would like to stop over here. Thank you so much.